All right, let's talk about half-life. Half-life of a radioisotope. This has really revolutionized archaeology as far as being able to date something accurately. And the way that they do that is by radioactive decay or isotopes using half-lives. I assume we have a picture here of maybe the Dead Sea Scrolls or something along those lines. It does look like Hebrew. But, I'm not an expert, so I'm just guessing. All right, so the half-life of a radioisotope is the time for the radiation level or activity to decrease or decay to 1/2 its original value. Okay, so if we look at 20 milligrams of iodine through the half-life, okay, then it becomes 10 milligrams, another half-life, 5 milligrams, 3 half-lives, 2.5 milligrams. It's much like getting divorced, if you will. You once had whole, and then you get divorced, and then you have half. Then you get divorced again, then you have a quarter. You get divorced again in an eighth, 16th, 32nd, 64th, 128th, so on and so on and so on. So these are half-lives. So it's the time it takes for the radiation level to decay. So if we know these radiation levels and we can find them in the environment, we can tell how long something has been there. So the decay curve is a diagram illustrating the decay of radioactive isotope. Okay, so iodine 131. If we look at it, it's not a linear decay now, is it? It's not. It's a quadratic decay. It's parabolic in nature. Okay, so we can just see how it decays over, in this case, days. All right, so it meets its first half-life at 8 days, and then 16, and then 24, and then 32, and 40, and it just drops down from there. So how do we use half-lives? Well, we need to state the given and needed quantities, all right? Just like normal organize. When plan to calculate the unknown quantity, all right? Write the half-life equality and conversion factors if we need to, and basically then set up the problem to calculate the needed quantities. That's our plug and chug, our plug and play. So phosphorus 32, a radio isotope used to treat leukemia, has a half-life of 14.3 days. If a sample contains 8 milligrams of P32, how many milligrams of P32 remain after 42.9 days? Remember, we need this number. This 14.3 days. That's our standard, okay? So state the given and needed quantities. Well, we need 8 milligrams of P32. We need to know that 42.9 days have passed, and the half-life is 14.3 days, okay? So we want to know the milligrams remaining, all right, after 42.9 days. So phosphorus 32 has a half-life 14.3 days. We know this, okay? We're going to plan, okay? So to calculate the unknown quantities, well, days, half-life, number of half-lives, it'll go through, and then the number of milligrams remaining. So we need to write a half-life equality and conversion factor. So one half-life, okay, is equal to 14.3 days, all right? And it doesn't matter if the equality is written like this or like this. They mean the same thing. All right, so basically we take 42.9 days times 1 over the half-life, okay? So we'll be basically dividing by 14.3, all right? And then we've got to cycle through the half-lives, all right? Well, we start with 8 milligrams, and then we have 3 half-lives we've gone through. So we cut that in half, and that gives us 4 milligrams. And then we cut that again for the second, 2, and finally the third. We are left with 1 milligram of phosphorus 32 after that, okay? So we need both the half-life equivalency, how many half-lives it's gone through, as well as our starting value to find our finishing value. All right, so these are naturally occurring radioisotopes, okay? Carbon-14, very common in dating. Look at the half-life, 5,730 years, okay? Potassium, if we can find potassium in something, 1.3 times 10 to the 9th years, all right? So strontium, uranium, all right? We're looking at very strong lengths of time, meaning that we can use these for dating purposes for very old objects. All right. Now, medical isotopes, on the other hand, look at the time frames. Look at what we're looking at. We're looking at 28 days, 8 days, 74 days, 44 days, 3.8 days. Okay? So we're looking at some very short half-lives. So just depending on our use, our application, our need, we'll refer to different radioisotopes. So radiological dating is a technique used by geologists, archaeologists, historians to determine the age of ancient objects. The age of an ancient object is determined by measuring the amount of carbon-14 present. Carbon-14 is produced in the upper atmosphere by the bombardment of nitrogen-14 by high-energy neutrons from cosmic rays. So we've got neutrons, cosmic rays hitting the nitrogen-14, bam, all right? Proton goes flying, or it's converted, okay? And then we get our radioactive carbon-14. So it reacts with oxygen to form radioactive carbon dioxide, which is absorbed by plants. The uptake of carbon-14 and CO2 stops when the plant dies. All right, so it continues until the death of the plant. As the carbon-14 decays, the amount of CO2 decreases. CO2-14 decreases at a process called carbon dating. Scientists use the half-life of carbon-14, which is 5,730 years, to calculate the length of time since the plant has died. And that makes sense. So if you are a paleontologist and your specialty is plants, ancient plants, well, this is a great way to tell how long ago this plant actually lived. All right? Hey, look at that. The age of the Dead Sea Scrolls were determined by using carbon dating, carbon-14. So how many years are required for the mass of 40 milligram radioisotopes to decrease to 10 milligrams if the half-life is 22 years? All right, again, this is, how can we set this up? All right, well, 10 milligrams from 40 milligrams. Okay, the half-life is 22 years. So, okay, well, if we cut 40 in half through one half-life, that would be 20. So we went through one half-life. And then if we cut 20 years in half, that would be 10, so 2 half-lives. So what would be the half-life? How do we figure it out? Well, it's 44 years. 2 half-lives times the number of years of the half-life. All right? So 40 times half times half. Okay, so you can do it that way as well. So if I was through 3 half-lives on this, we'd expect 5 milligrams. If I was through 4 half-lives on this, 2.5. And it would be, 40 times half times half times half times half is 2.5. All right. So it says write a half-life equality and conversion factor. 1 half-life equals 22 years. And then they multiply it back into 44 years. Pretty straightforward on half-lives.